So why would we estimate population size? Well, typically we look at it as kind of being a baseline approach. So what does the population look like now? And then in the future, we can compare what those populations look like over the course of time. We typically look at estimating population sizes on a couple of different levels. If it's a large organism, so if I asked you to count every giraffe on campus, it would be a fairly easy thing for you to do, right? There aren't many of them. So that would be something we refer to as a direct count. But if I asked you to go to the mall and count every ant outside of the mall in the parking lot, it'd be a much larger feat, right? You probably don't want to try to count every ant in the parking lot at the mall. So we do things that would allow us to subsample, get a count, and then do what we call extrapolation. So essentially what you're looking at is estimating a population size. So a direct count is going to give you a much stronger number. Subsampling, extrapolating is going to give you an estimate of the population. Sometimes that's good enough. We don't need to worry about larger or more direct counts in that regard. So for estimating population sizes, often we use things like bird calls. You don't always see all the birds, but trained individuals can estimate the number of birds in an area based on the calls. Things like animal droppings. Any animals that are skittish, tend to hide from humans, or are nocturnal, we'll actually just count droppings to see how many are in an area. And so what we want to think about is, how is that population changing over time? If organisms are dying, how does that affect it? If new organisms move in, how is that affecting it? So that J curve that we mentioned shows this kind of natural sort of slow growth at first, but then the population really takes off. And what we look at is, this isn't going to go forever, okay? We tend to look at this as being a growth form that is eventually going to kind of top out. So we can't say that every population is going to continue in infamy growing forever, right? But what we can look at is that if we put a limitation on this, like environment, we get that S-shaped curve that we mentioned before, so limited by K, and we get an interaction between the population and the environment that's actually going to keep it from growing anymore. And so here's our S curve. And this is really more natural in a population. We would expect something to be limiting this population, particularly something like food resources, changes in temperature, predation, toxic waste, those sorts of things would certainly limit the population growth and how well it's doing. So we can look at these changes in growth patterns a couple of different ways. Typically, we look at actually C down here at the bottom as being the most realistic. You kind of start out growing nicely. Something's going to limit you in the environment. Your population drops off, and you sort of do this fluctuation around K. And without any significant changes in the population or environment, this is the way it's going to continue, sort of this fluctuation about K. So when we look at changes in these populations, what we're really interested in is how the populations impact one another, particularly in a community structure. So we want to know, how dense is a population. So we start looking at these numbers of individuals per area or volume. Volume, of course, if you're talking about aquatic animals, right? So we want to know about kind of local densities. How are these organisms dispersed across their habitat? And often we see them sort of in these clumped formations, Many organisms tend to kind of group together, often for protection, and so we get these sort of patches like I have here with my starfish, the dots representing individuals, and so they kind of have clumped together. You get a couple of loners, but in general they're in these little sort of sub-clumps of the population. Some individuals will tend to scatter evenly. It's unusual to find organisms in nature that do this, but humans tend to do this quite readily. We spread out, like on our beach picture here, sort of evenly. Sort of that idea of personal space, right? Giving you space around where you're sitting, in this case on the beach, giving you room to play. But other organisms, depending on how they're pollinated, how reproduction goes, can get these very random patterns. The dandelions coming out this spring, we certainly look at their distribution throughout the spring and summer and fall as being very random, really depending on which way the wind blows, right? If these are wind pollinated and wind dispersed, the location of the seed for the next individual is completely dependent on the wind. So you get some that are close together, some that are very far apart. This is important when we start looking at the interactions of these species with other species, so competing for resources and so on. That carrying capacity that we mentioned, I wanted to show you in the sense that we look at this maximum sort of population density, and that fluctuation around K, as we mentioned, is very, very common in organisms that are larger and produce very few offspring. You sort of reach a maximum that the environment can sustain. Our selected species, on the other hand, are something we refer to as an opportunistic species. And these are things like your flies, many of the insects. So they do really well as they reproduce in very high levels, but most of them are not going to survive, right? So then the population falls back down. The few that do survive find a good food source, a good habitat. They reproduce like crazy there for us, and then we continue, population going to drop off again and back up again and so on. And so these are selected species. R is reproductive rate. So really the population is not limited by any resources. It's limited sheer by the number of individuals it can reproduce and how many of those individuals actually survive. They tend to be pretty small individuals with lots of offspring and tend not to care at all for their offspring. Now, when we look at these fast reproduction rates, so R tends to be a very fast reproduction. K selected species tend to be slow reproduction or gestation times. And then there's this kind of group in the middle. And we've got to keep in mind, this is not bimodal. We don't shove populations one way or the other. They're often in a constant state of flux along this line of how well they're doing. And so our birds here in the middle, we actually look at them dying really at any point in time. So on our survivorship curves, our flies, as we talked about, many of them tend to die when they're very young. Very few old-aged flies. Elephants, on the other hand, because they take such good care of their young, this would also be humans and many other of the large mammals, take care of their young. Many of them, if they survive those first couple of weeks, are going to live to old age. Birds, on the other hand, squirrels, things like that, tend to die at all ages, right? They do risky behaviors. Birds flying into windows, squirrels crossing streets. It doesn't matter how old you are in that instance, you have the potential to die at any age. Now, I understand humans have the potential to die at any age as well. However, what we typically see is we do live to the ripe old age. Now, pushing the average old age of about 80 at death, right? So here's our human population curve, and I don't think this will surprise you. We started out very low, of course, and kind of started on this J-shaped curve. The question is, do you think it's going to continue that way? Today we sit at about 7 billion people, which actually on this graph we've missed the mark a little bit, right? So we actually we're sitting at about 7 billion, but we were actually never quite this high. So the curve actually started to come down a little bit sooner. But if it's going to continue to come down, we don't know, because actually the human population is still growing very rapidly. Even though it doesn't seem that way in places like the United States and Europe, we'll look at other countries later on where the population growth rate is just going to astonish you.